I haven't been pretty much on time, so we'll see. Okay, so, today I will, talk about collisions. Actually, I wanted to talk about one thing beyond collision, which is, to actually probe and control ultracold chemistry. And sort of the goal here is, we're all very much into quantum mechanics. So we think about chemistry as a quantum mechanic transformation of reactants to reaction products. So like what we wanted to describe here was to describe it was, wave function. Now, let me give a little bit of historical perspective, sort of more on a chemistry perspective. So this is a very nice figures from the lecture by Dr. Hirschbach, who is a colleague in the esteemed colleague in the Harvard Chemistry Department. And the perspective here is that chemistry, this is in the this is the axis for the 1900s, where it is a field where physical chemistry is a field to understand chemical reaction in terms of initially in terms of its rate. By burning things, you start to learn something about the chemical reaction, what's important and what about the rate. And of course, that predates quantum mechanics. And where it comes in, it really starts to people start to think about sort of wave nature of that quantum mechanics comes in actually explaining sort of molecular bonding and things like that. But people can also take advantage of wave natures wave nature of matters to do detections, where now you can start going to probing the structures. And for example, from diffraction, kind of X-ray diffraction, people are able to figure out, obviously, the double helix structure of the DNA. So these things are all kind of static. And then sort of the next thing on this time axis is to start probing dynamics. And by that, that's where actually Hirschbach and others made their contribution, was to really figure out ways where they can probe reaction with single collisions. So usually in these kind of scenario, collision happens and then subsequent collision happens, and it's really hard to isolate these elementary steps. So Hirschbach and others have built experiments such as this, molecular beam experiment, actually cross molecular beam experiment that allow, in some sense, dilute gas traveling in one direction and the other direction to collide, such that they only have a chance to collide once, and then they're able to probe what happens after that. In fact, the kind of reaction that they probe is not very much different from what we're doing. They were doing alkali atoms or alkaline halogen and things like this, where you start with these kind of reactants, and then you have this atom exchange reaction at the end. Okay, but of course, sort of in some sense, the goal is to continue climbing this mountain to have a complete characterization. By that I mean pointing to this angel who holds a side-shaped arc, and who may be a here who can calculate, basically using quantum mechanics to figure out using quantum mechanical language to figure out what should happen to a chemical reaction. And I will say that actually we are now able to characterize this one reaction with a completely mention that regime. Okay, so before I get into what I really want to talk about, I'm just briefly surveying, and this is just picking a few examples of different sort of cold chemistry experiment or chemistry experiment with cold molecules. For example, there have been work in different labs where bring these molecular beings more in co-propagating friend as opposed to these initial cross molecular beings and allow to tune the energy on these are from different experiments, tune the collision energy from close to zero to something larger. So then you can really tune the scattering energy axis and observe collisional cross-section, and you can compare that to theory, the calculation of quantum chemistry. And in this particular example, they were able to show that what usually considered as the gold standard in quantum chemistry is CCSV. It's CCSV parentheses T, but they're just including different level of electron correlation, and they probe actually it require additional terms in additional correlation, consideration of additional correlation and to be able to match their experiment. So this is just one nice example. One can also, this is actually another kind of molecule that has been talked about, not this particular one, but these kind of metal plus a ligand and metal center plus something else, and it's really in a way in this paper they sort of synthesized these exotic chemical species, but perhaps they have actually been used because of the cycling properties. And what I will be telling you about is directly probing the chemical reaction in this and related work. Okay, so let me give a brief outline. So we can totally control molecule quantum state, and this is using association technique that we have already introduced during this school. And from there, actually, lots of things that are very surprising. Now I think many of you may be entering this field now or in the last 5 years, but when we really started long ago, none of this we expect to happen. So don't get into that. So first chemical reaction at ultra-low temperature, that seems to be really bizarre. We see chemical reaction goes out in slow motion, and doesn't allow us to probe very accurately, but that's really also a surprise. We can steer this reaction with light, I briefly mentioned about this, and we can even control the reaction product because of we have conservation of nucleus beams, and we can completely characterize this one particular example that I'll show you. And then the surprise didn't just start without we understand it, and then with the simple atom molecule collision and reactions, things are off and quite worse negative. So lots of surprises. Let me just start by talking a lot about the fluorocarbon experiment where a trapped gas or molecule in a single quantum state, all of these can be preparing the ground, these degrees of freedom can all be preparing the ground state with a relatively dense, close to quantum degenerate gas was made in 2008. And the first surprise was that they didn't really live as long as we had hoped, which would be the vacuum lifetime. For that apparatus, it would be about a minute, but rather they're actually going away in pairs and with a lifetime of order of seconds. Now, I like to show this, but I don't get to show this very often since I'm only talking about the therapy experiment. This was, after 10 years, we thought we were very close to quantum degeneracy. We were only phase-space density of 0.01, where quantum degeneracy will be about 1. It really took another 10 years to get to quantum degeneracy, and these are sort of a collection of photos of people who have worked on sort of the KRB page from when we started, and I don't know if you can see where I am, but from when we started to this picture. This was the 2019, so I'm over here. Okay, so we don't expect, naively, we don't expect chemical reaction. We usually expect chemical reaction to see the ultra at low temperature, and that's what the intuition we have. But why does it even happen? Well, it turns out the kind of species, the kind of molecule that we're working with, it turns out it's a downhill process and therefore nothing really stops it. By that I mean, if we write sort of, if we draw sort of schematically energy versus some kind of reaction coordinate, the potential energy surface just keeps going down. I mean, there are some bumps on the way, but there is nothing really stop it from going proceed to the lower energy states. And that's the reason that one could expect chemical reaction to, it's not violating anything that chemical reaction can happen. And usually the way we were described in this, for example, in this picture, is that you start with some reactants, some kind of asymptotic, and then you prepare them, they're far away, and they can come through these attract through these long range forces, and these are all the different kind of forces that they can experience, get to the short range. Actually, before that, sometimes there's potential energy barriers, but they're relatively small on these kind of energy scale to get into the short range where they can really exchange their the atoms, for some time, and then comes out as a reaction product. Okay, so that was the explanation, even though nothing, what was observed here is really just loss. Okay, so there was only loss, and then subsequently there's many other experiments, as Simon has also discussed, that even when these, let me see, I didn't have that, but even when this potential energy surface at the end supposed to be go up here, and therefore product is not expected, then the same kind of two-body loss was still observed in various systems, and therefore we really need to really figure out what's going on. We need to have a direct detection. So that was one of the projects that, yes.
So in the previous plot, the molecules are at the lower depth of the potential field. Can I understand if the energy is converted to kinetic energy, or how do I understand where the energy is distributed?
Yeah, so that's more of a classical picture. You're thinking, I think this row like this, but in reality, what happened is the energy, the whole time, the energy goes like this. Okay? So this is how we proceed. And then now the question is, that can be in different forms. For example, over here, it turns out the kinetic energy is still very small, but they're internally very excited. Because the bottom of the potential is down here, so they're vibrationally excited, rotation excited. And over here, when you really come out here, if you come out, ultimately, depends on the internal excitation, then the rest goes to kinetic. But you can also think classically, there's a ball rolling downhill and goes down that way. But in quantum mechanics, we are always, energy does conserve. It's just that it can be distributed to different degrees. Okay, so now in order to directly detect, we bring together, in some sense, techniques from different fields. What we can do, up to that point was to observe, create a molecule, observe loss, but unless we know what could happen to it, it's hard to really test what actually happened to it. To really see it, we employ, we wanted to use ion spectrometry. We can, for example, ionize these clouds and arrange our ion lenses in such a way that, first of all, just to time apply, we ionize it and then push through electric field onto our detector. To time apply, we can get the mass information. This is when it arrives. And we can also arrange these electrodes in such a way to be kind of ion lenses, and therefore get spatial distribution, kinetic energy information. So this is useful. Yeah, actually, all of those, it turns out these tools are all useful when it's being used in a complementary way. Okay, so we didn't know that chemical reaction actually happened because all we had up to that point before we built the apparatus was that we just block. So it could be like we build the apparatus and we see nothing. But it turns out, luckily, we saw a lot of it. That's very surprising, of course. So it was a really big risk, but it also, we putting a lot of different kind of tools, and it turns out, some are redundant at first, but it turns out they all ultimately complement one another, even the law information. So that's something to consider when you're perhaps building an experiment this one, especially if you don't know what you expect. Sometimes you need a lot of backup scenario. So we combine our sort of AMO physics apparatus where we know how to make molecules with these physical chemistry probes of ion spectrometry. And this is what the lab actually looks like. In fact, I have this other lab, and the other day I walked in, this cable is even messier. So this is actually the clean lab. Okay, so to probe the reaction, what we do is, we prepare molecules back then, and it's already been discussed how one does that. These are bioalkali KRB molecules. We can have on the order of 10,000 molecules at a temperature of some microkelvin, and as we talked previously, that they just goes away. Okay, so to probe them, we can, with ion detections, we can come in with our UV laser to ionize our samples in these kind of repetitions. The whole experimental cycle takes 1 minute to repeat, and therefore we want to be able to probe many shots during that one experimental cycle to collect these things. Okay, so once the apparatus was finally built, and this was like after 44 years of hard work, then we were indeed able to see species such as K2 and RB2, K2 and RB2 separately, and that's what we expected as chemical reaction products. So we were very happy, but we had to be very sure that these, because when you have a sample of KRB and you have some atoms, it could be that you just have K2 and RB2 flying around, and these coming from our reaction that we're thinking about. So we had to do a lot of detective work, and this one is actually relatively straightforward. The next one is actually was quite fun and puzzling. So first of all, on our detector, it just KRB just show up as a single dot because it's very cold. These are ultracold molecules, and they're just very cold. They basically have zero momentum or zero velocity. So this kind of tells us about the resolution of our detector. And then when we look at our K2 and RB2, which they show up at a different time when they're kind of flying on mass spec. We can also get their kinetic energy distribution, as I mentioned, that we have these ion lenses, and they have different sizes, and that's significantly bigger than this KRB initial cloud. So this does carry kinetic energy. And we do expect that, if these were to be the product, that the potassium dimer and the rubidium dimer is going to fly away with equal but opposite momentum, and therefore from here we can get the ratio, which we expected to be actually inverse of the mass. If we can work out one lines of math, and then that works out. So that tells us, okay, this indeed, with this amount of evidence, it is coming from this is coming from the reaction. I think we also did something else, and actually we even use donut beans and stuff like that. I'm kind of forgetting now. Okay, so in fact, we do have this chemical reaction that we prove from, not just seeing the product, but making sure that they have the right kind of momentum. But if you squint in this mass spec, you do see other things that we didn't expect. For example, K2RB2 and KRB2+. Okay, so these are triatomic species which are energetically not allowed to be produced through the neutral chemical reaction. But nevertheless, they are actually real signal, and we can also see their kinetic energy distribution. It turns out to be even bigger. So where does all this energy come from, and where does the species come from? Okay, so this, yeah, so basically, they have a kinetic energy that are sort of on the order of 10,000 times, sorry, 1,000 times bigger than our K2 and RB2 products. Okay, so we hypothesized that, you know, what else could be happening? Maybe these are the complex. Even though we heard that they should live for a very long time, we still didn't expect to see them because these pulses are sort of nanoseconds duration, so we just didn't really think it was possible. But nevertheless, we did some more detective work, and we think they're from dissociated photoionization, meaning that, you know, when we ionize, so this is the potential energy surface, when we have a complex here, if we can ionize it and we come in with quite short wavelength in some sense, you know, we can go up to, you know, say above 345 nanometer. They have a chance of actually breaking up into, you know, triatomic species as we would see it on our detector. And so we can change that wavelength. So we can start from really high up and go all the way down. And we see that this sort of distribution actually shrinks, and we can do some statistical analysis on there and see that at some point we indeed, I mean, we still see these species a little bit, but we indeed see that the size shrink down and kind of correspond to where this threshold of dissociation stops. This turns out to be, you know, later we understand to be the atom molecule collision, which is the number 5 point. This small background. Okay, so from there we were able to to be confident that these are actually reaction complex that we detected. And if we were to reduce the wavelength here, and we were able to see directly K2RB2 complex, these K2RB2 ion directly. So we were very excited about because it was completely a surprise to us. Okay, so that was actually this was all collected in 2018. We published in 2019. But how do we understand these complex? You know, this has been talked a lot about, so I won't go into too much detail. Again, you know, the picture, as Simon has shown from inspiration of John, is to have, you know, this fly goes into the bottle. This is a very, very deep potential well, and this is actually relatively small energy gap, small energy outgoing channels that basically, if you were to probe, you know, I think this is slightly different. Okay, so the fact that we prepare such cold gas or molecule, limiting the number of channels, or, you know, there's nothing up here, and this actually itself is also very small number. One could use RKM theory to make basically a time energy uncertainty relation to kind of get a rough idea about these complex. And John had predict perhaps 3 microseconds. Thai experiments and others that predict, you know, with a revised number of perhaps 0.1 microsecond. And experiments at this point, we couldn't really distinguish these two numbers yet because we don't really know the ionization cross section, but we were able to sort of estimate, you know, the lifetime will already be basically within this range, but not differentiating the theory. Now, the challenge to directly measure this is in the following way. We have sort of second kind of time scale for the molecules to collide and form a complex. So that's very slow, but it only takes, you know, perhaps this microsecond time scale to break up, right? So how do we initiate that time 0 to see the complex build up is the challenge, but it turns out, as we found, and also, you know, it was also inspired by the theory at the time, was that these light that we use to track the molecules can actually initiate, in some sense, you know, initiate the complex buildup because they clean out these populations. And I should say that in the previous experiment, we took care of actually turning off our optical dipole trackers. We wanted to prove that the chemical reaction product, you know, we want to have as clean as possible scenario. So we were chopping our optical dipole track for those experiments already. Okay, so now if we can clean out these population and then just see them build up, we can measure directly these complex lifetime, and that was to measure to be about 300 nanoseconds. Okay, so this actually compares well. Thais actually did a more careful calculation for KRP specifically when we get these data. And this again, actually, it's not that far from his kind of rough estimate, and then also sort of about factor 2 different, just like in Simon's case. Okay, so in some sense, the fact that the complex lives for a very long time is my second point here. Is kind of like reaction is playing out in a slow motion, and in the future we would like to probe that directly to some other means, to kind of get structured information. And the fact that they live for so long, this light that we use to trap the molecule can steer them to a different reaction pathway in the sense that they sort of excite these complex, which is not a handle that you usually have in a typical chemical reaction, because that's usually a very transient effect. Transients it's usually a transient event, and you just never really able to, like, it's very hard to actually keep the complex, and that's actually its whole field, because the complex is a very critical stage between for the reaction to transform into product, and therefore that's actually something where it will tell us a lot about chemical reactions. Okay, and then actually what it will tell us is something about the product, because if it has a lot of time to, these atoms has a lot of time to find each other and then figure out how to form their product that comes out, one does expect probably a statistical distribution of the chemical reaction product, as opposed to it has to come in exactly right angle and bounce off, and then that we would prefer chemical reaction product, as opposed to they have a lot of time to do all the things that they want. Okay, so that's something that we could test, and in fact, this is actually already the points on this slide. So to really study chemical reaction with these quantum mechanical, ultimate, quantum language, what we're talking about is that usually you calculate very accurately the potential energy surface, and of course this is multi-dimensional, and then you do perhaps quantum scattering calculation to figure out what are the probability of landing into a particular quantum state. So you ultimately need the state resolved reaction rate. So that has probability going to different quantum states, and that's what we will ultimately probe. But it turns out, even for these 4 atom system, the state of the art cannot exactly predict what happened, because it's like I said, multidimensional and very heavy atoms. So this cannot be done, but we can compare to statistical theory in the sense that because we observe such a long-lived complex, we expect that every possible energy state is probably going to be equally likely to be populated. So that's that statement. Okay, so what are the possible quantum states in KRB reactions? It turns out there's only 10 wave number, which is 10 Kelvin, which is 300 gigahertz. So very small, almost thermal neutral, is a very small amount of energy. It couldn't lead to any vibration excitation, and only rotation excitation. So that eliminates sort of possibility already. But for rotation excitation, it can still go quite high. So for example, potassium, just given by the rotation quantum number, could go to K2 of 12 and KRB 2 of 19. So we need to really, we want to see the product, we want to get the quantum state of the product, we need to have a way to detect the quantum state of the reaction product as they fly out. And the technique to do that is also a physical chemistry technique that's well known, is use this resonant enhanced multi-photon ionization. So that's a mouthful, but what it is that we can first drive a transition that give us state information. So the transition can only be driven if molecules are in a particular state, and then subsequently ionize that. So this allows us to get the state information. And when we did that, so each one of this is, spectroscopy, but we already know from, older literature, so we can go there and search and make sure we park on the peak of the transition line, so to allow us to have the best sensitivity. When we do that and go through all the possible rotation state, we find this interesting parity. For K2, we only see even rotation state, and for RB2, we only see odd rotation states. Okay, and this actually suggests something, which is that the nucleus being complete. And why did I talk about that? Well, it turns out, if you think about two electrons, there is the spin degrees of freedom, there is the spatial degrees of freedom, being in orbit. And for these molecules are homonuclear molecules. They also have those 10 to the degrees of freedom for their nuclei. So we have to consider the spin of the nuclei, which also has to respect the quantum statistic of the nuclei. So the spin degrees of freedom and the rotation degrees of freedom are kind of together to form the wave function of the nuclei, part of the wave function. And for and let's just say for K2, it turns out these, despite that they are usually fermionic atoms, their nuclei are bosonic, and so their bosonic nuclei has to allow transitions are total wave function has to be symmetrized, so symmetric. And if you start with a particular nucleus spin, and then after, say pointing down, let's say, and then after the reaction, if their direction still remains, then that's a symmetric spin wave function, and their rotation wave function has to also be symmetric. Well, in a rubidium case, the nuclei are fermion, and therefore, the symmetric spin wave function will lead to an anti-symmetric rotation wave function. So this is why we saw, this is, the fact that the spin turns out to remain in their orientation despite the long, complex collision and stuff like that. We see this strong parity factor. Okay. Any questions? Okay, so now this also allow us to leverage the fact that the nucleus spin is not changing, so there's something is not changing, and therefore we could control the outcome by controlling the nucleus spin. By that, I mean, if I start with nucleus spin superpositions of, one atom and the other atoms, after the collision, we know the spin direction doesn't change, but they had to pair out differently. So we could have an outcome where both even and odd is possible because, we start with pointing one way and plus pointing the other way, so that there's many different combinations. And this could lead to, both even and odd for the potassium dimer and also odd. Okay, so this is a knob that we can change by simply changing the magnetic field. So on the left-hand side, we can change basically the superposition of, alpha, beta, gamma can be changed by changing the magnetic field of our experiments. And we expect to see symmetric, anti-symmetric combination through this pairing. And we expect as a function of magnetic field to go like this. And this is indeed what we saw for potassium dimer in one way, and then for rubidium dimer in the other way. So in a way, we can control the outcome in terms of their parity state by simply changing their nucleus spin superposition as a starting point. Okay, so that's a bit of a surprise after we learn about the complex, because it turns out something still conserved. It may or may not be a surprise, but it certainly is something to be checked. Yeah.
Sorry. So in the previous part, you said like you can control the current molecular PRB nucleus spin and like adjust the product rotation distribution.
Yeah.
So like is there a way to like we basically tune the specific rotation of the number in the problem.
Yeah, so that's a different, yeah, so this only changed the parity. To control the rotation, that turns out not possible because this, because of the language. So that's a different degrees of freedom. So like, what's the branching ratio of going into different rotation state? That, has to do with the complicated collision, which is the. Yeah, and which is something that we'll talk about in a moment, okay? So, so that's actually interesting in the sense that you can imagine, so in the future direction, you can prepare them in just the right superposition initially for the KRB. And then through the collision, you have a way to separate your potassium and your rubidium and pair them up. And this could potentially, if coherence is preserved, it's if the coherence is preserved, which needs to be checked, you can imagine that the potassium dimer and the rubidium dimer ultimately could be entangled through their nuclear degrees of freedom. So that's something we will be very interested in the future. And that certainly has not been done before. Okay, so now going back to talk about chemical reaction as a quantum mechanical problem, scattering problem. What I've shown you is that we are able to collect these data to show the reaction product distribution. But this actually is different from the state result reaction rate in the sense that I don't know when my potassium dimer is landed in this particular quantum state, what is the corresponding rubidium dimer? You know, like there's a distribution. So what I mean is that I need to simultaneously detect, you know, the potassium dimer, rubidium dimer come from the same chemical reaction, as opposed to, you know, accumulate data for independent, in some sense, independent events. Okay, so that's the new ingredient that we need to really fully characterize the chemical reaction. And that means we need this thing called coincident detection. So we need to be able to say, when I detect my potassium dimer in this state, the rubidium dimer in the other state comes from the same reaction events. Okay, so this we will leverage again, this momentum conservation. Okay, so we can simultaneously looking for potassium dimer or rubidium dimer in a particular state. And sometimes we have potassium dimer and rubidium dimer come in that when we look for it in the same experimental quick run. But in order to make sure that they are coming from the same event, we utilize the conservation of momentum. You know, they have to come, they have to fulfill this requirement of equal and opposite direction of momentum. So we have again X, Y, and Z direction, sorry, X and Y spatial direction, and Z is the time of flight axis. So we can put filters on it. On the X and Y, you can see these are all the pairs landing in a particular pairs of rotation state, but they're not necessarily all correlated. Sometimes they just, you know, I detect a potassium dimer here and rubidium dimer we didn't detect because, you know, their detection efficiency. But once we apply this conservation constraint, we see all the pairs, you know, we screen out the ones that don't line up and only the pairs that satisfy this and allow us to collect the count. So this allows us to know like which pairs are coming from the same event and we can accumulate the count. Okay, so actually I'm doing pretty well in time. Okay, so in order to compare to this statistical model, which means that every single quantum states are equally likely to be populated, we need to be able to count those quantum states. And it turns out these quantum states are not just counting of the rotation states of potassium dimer and the rotation state of rubidium dimer. There is one more angular momentum. That is when they break out, there is still the orbital angular momentum relative to one another. Okay, so it turns out what we measure, we only measure two, and then, you know, there's many different ways of getting us to those two. There's many different, maybe let me back up. So what we know is that initially the molecules are in rotation ground state. and they're colliding with 1 unit of partial weight because these are fermions, so that's the lowest energy partial weight allowed. So the total angular momentum of the system is, added all together is 1. And when they add to the products, we have the rotation compensate of of the two separate molecules, but there's the orbital angular momentum as well. So the 3 vector has to add up to 1, and there's many different ways of adding up to 1. You just know 2 of them. Okay, so these are the different ways, and usually you will have a lot more ways if these 2 rotation quantum numbers are similar and large. And for example, like on this corner, you have these numbers that are really large, and then you have very small number if they are just small or they're very different. Or you imagine, there are 3 vector has to add up to 1, and 2, and that's sort of the rule. Okay, so now, so putting this together, together with the coincident detection, we can start accumulating data, and the statistic is relatively low. So each channel here, we accumulate for about, several days, and there are 57 channels of them. So the experiment kind of run like for 2 or 3 months continuously, and this was kind of after we were able to return to the lab after COVID, lab shut down that everybody had. Maybe some of it done because before the end of grad school. But anyway, so the experiments are running remotely, so the students are sleeping. So no problem. Okay, so with that, we were able to create. To have this map of all the channels, 57 channels, and you do see sort of more population. This is a 3D plot, so population is in the z-axis. You do see more population at this corner where you have larger rotation quantum numbers and smaller difference between the 2. Of course, we want to scrutinize our data carefully, so we compare to this statistical model. And we can do sort of row by row, and then these are just all the comparison, which is, perhaps overwhelming. But if you were to squint, you might see this one channel where we have, almost no measure, no measure count, very low measure count, but the models predict a very large count, number of counts. Obviously deviating. And this actually has a simple reason and actually a nice reason. This is actually, I show you this reaction coordinate energy on the reaction coordinate. As the reaction proceeds, it eventually breaks out to the product. And this particular channel is the channel that has the highest internal excitation, the smallest kinetic energy to come out. Okay. And it turns out at long range, there's an angular momentum barrier, and it just, most of the channel it's gonna come out. And therefore, there's a suppression. And so this is sort of breaking up the molecule, and it turns out it's not enough energy because when they break up in the long range, there's this barrier, and then they have to come back. Yeah.
So now you have the ratio between the statistical thing and the measured thing. So is that ratio given by sort of LBD?
You mean here?
Yeah.
Yeah. That's right. So this allow us to determine the barrier timeframe clearly. This is the insane basically. Yeah. But also I should say that it also, they are, so for those, and then there are actually channels. I don't know if I have theory on here. No, I don't. Channels where they're angular momentum, because there's many possibility again over here. So there are channels where they just really pass, and then there's channel where they really have to tunnel. So it's these signals are mostly coming from the channel where they just pass on. The tunnel aspect is actually very small. Okay, so there's one channel that we understand, but it turns out we can do this sort of p-value statistical analysis and find that there are 6 other channels that deviate statistically significantly, but we don't really know why, because we don't really have a theory. You know, we now go beyond statistical, obviously, and we need theory to put that. So we know the right answer, and anyone wants to figure out how to calculate. So it's, again, it's a computational intensive problem. So, I guess this is just to motivate that, new development in theory, you want to calculate methods of calculation. Okay, so I still have 15 minutes, I think. I can reduce it. If we can reduce it. So this is a bit of a summary of kind of all this KRB reaction that I was talking about. It was actually work of a team, but mostly the apparatus was built up by a PhD student and a postdocs who are both moved on. So this is one PhD thesis. Now, so we feel like we get a really good handle on the KRB reaction, KRB plus KRB reaction. But what turns out the next thing that we do is, okay, so maybe theory cannot deal with molecule in 4 atoms. Surely they can deal with atom molecule, because less number of particle and more tractable. So let's just try to look into there and see what we can measure quantitatively, and then hopefully we can compare it. So it turns out that's the experiment we do for KRB plus RB. And in this case, chemical reaction, the two-body chemical reaction is energetically forbidden. So one expects to see some complex, potentially, depends on the time scale. And then, but then these complex should go back to the reactor initially. So that's just, there's only one open channel in some sense to get into the short range and come back out using exactly the same sort of theory. And from the estimates of the density of state, so it turns out density of state is much, even though n naught, so the number of channel is reduced to 1 compared to previously in the KRB case, maybe about 300. The density of state is also reduced significantly because we have now 3 particles as opposed to 4 particles. So again, we expect time scale now shorter, than this. Previously, we have in the KRB plus KRB measure at 100 nanoseconds, and now perhaps 1 nanosecond. But when we actually measure, it was even longer. It was 300 microseconds, and this is 5 orders of magnitude different from, this initial.
Only 3 orders of magnitude.
Depends, yeah. So John was saying number probably not quite.
He screwed up that.
Yeah. So and of course we want more dramatic effect, but John's 89 is probably not right. So compared to the 1 nanosecond, different by 5 orders of magnitude. So what can we say about that? Well, so this was work actually done. I think 2022. I feel like it's much longer than that. But anyway, so maybe you just got published 2020. I feel like it was earlier. But anyway, so we were like, what else can we know? What can we do experimentally? Because theorists had to come up with an explanation. And what can we do? Not yet. Okay. What can we do experimentally to give us more information? And the nice thing about our experiment, we can see what happens. Kind of see what happens. At least, there is complex, and these complex can photo, excite, but nevertheless, we can measure super long lifetime. And of course, this is very different from what we expected initially. So what else can we do? I guess what I didn't mention was that these atoms was initially, prepared in the lowest hyperfine states. So 1,1. We can change the hyperfine state of that atom, for example, to 2, and we almost see no complex. So we see loss, this is when this is what we can probe on the molecule, but not using ion, they're both lost, but in terms of complex, they're very different, like 1, and you see a huge amount of complex at these kind of time scale, 2, you don't see complex. Okay, so what could be happening? For example, 2, the difference between 2, and 1, is that 2 has this additional hyperfine amount of, these energy of hyperfine energy, and that could be sufficient for the KRB to get rotation excitation, energetically allowed. So, actually, I'm not sure how many channels there are, perhaps this is the right number. So perhaps this could explain why there's no complex. But we could go look for then. It's not an easy experiment, of course. We had to detect these KRB molecules in these states and then flying away. But we could try, and the way that we do it again is to do these Rampey detections, these photoionization, state-sensitive photoionization detections. Not going into too much detail other than to say we had to take care of not ionizing. We wanted to be able to catch the ones that flies out with some momentum and not just ionizing our reactants, I guess. So we had to put a dark mask to avoid that. We can detect, in general, angle to 1 and angle to. This is just spectroscopy to figure out, how we would do the state-sensitive detection, and for rubidium we can also detect using. So we can look for that much smaller number than doing absorption, which is a more typical way of these quantum gases. Okay, so Ishan actually here is took this data, it did a lot of work. We were able to see, in fact, there was indeed angle to 0. Sorry, indeed, we're able to measure branching ratio going through the different rotation excited states. So this certainly explains where they go in some sense. There's these loss mechanism, and they, as a function of the added number, we can see that these ion counts grows for all the different possible channels, and further sort of confirm that these things correlate, and therefore this is a mechanism of a spin rotation outcome to after the collisions. Okay. So I won't go into too much detail. It's very much work in progress together with Timur and John for discussion, and basically, we want to we now have nice data. We want to understand why the branching ratio is such. But one thing, without going into too much detail, is that Timur provided a calculation to say that it's definitely not in the long range. It's not a spin rotation coupling in the long range. They have to get, because that rate is for 2 orders of magnitude lower than the loss rate that we see. So they have to get into the complex, and then it comes out with these, spin rotation. Okay. So maybe that will shed some light to the maybe some assumption that was used to count the number of states initially for this comparison of simplified, but we don't really know. What other things we can also change? We now have these 2 different scenarios. What about 1, 1, and 1, 0, 1 minus 1, and we have data, and I won't show it to you yet because we don't really have understanding. And there we do see, again, I guess now we do have data to show like they are actually complex. The lifetime is slightly different, and can we understand that? We hope, yeah. So perhaps we have a way to, I guess ultimately we're interested in from the angle of chemical reaction, is that perhaps we have a way to complex by controlling the chemical reactants and somehow change something about the complex. And first we had 1%, then perhaps or and then that makes a different outcome. So I think I'm actually record now. I'm 54 minutes, so I'm just gonna stop there and take it out. Yes,
Question about the nuclear in conservation.
yes,
So there you showed that there's a pattern very clear. I also noticed that for the heritage damage, student any population, there is some very small population, I think real or.
yeah, so. Right, so that's a good observation. So basically, what I can say is kind of in this picture. So, we were at 30 gals. So you do still expect a little bit of something else, and we do have a sensitivity of something else. So it's not, I mean, it's still in line with nucleus being conserved. It's just that the superposition of the initial state is not purely one, but actually it's like, this shows you like how much it is in this other one, and therefore this other area. So if we're at much higher magnetic field, then those will reduce that further.
So then there would be, let's say another way of thinking is.
That actually breaking the nucleus ring.
Yeah, that you come.
Yeah, I think that's harder, but that would be very. But that's yeah, that's not certainly not like right now we have a simple explanation.
And that's really like the RCS experiment that they do see difference for the different hyperfine levels.
Yeah, but those are lost. Right, so I guess that's hard to say. Anything that, yeah. Yes.
You can max select the complex. And having done so, you also something like full exposure and
Yeah, so we thought about it actually, it's as crazy as it is, but it's very difficult because, you will have to collect all the freshmen. And that just seems like very low. So instead, what we're going to do, I don't have any plots here. Instead, what we're going to do is that when we ionize these complex, there's also the electron. And the electron can carry also similar kind of information. So we're going to turn our electrons the other way. We're going to eject the electron, carry the mass energy of the electron. Like this is kind of spectroscopy of the complex and have try to get structural information. Yeah. So, yeah, I mean, I'm looking for reason to.
Well, this nice experiment with K2 coming out. How does the nuclear spin like spectator role? How does it play into this mechanism? Is it because like there's some recent calculations by Tom that show that the nuclear spin changes quite dramatically. May not be spectator, but maybe kind of like as they separate, it starts to be spectator again and kind of.
Yeah, so this kind of puts balance in some sense of what those companies actually be forward to, in some sense, because we know the complex lifetime. So there's some time scale, and then during that time scale, there is, coupling has to be smaller than one away from that, like one of the inverse of that time scale. So we kind of put back on, like even if there's coupling, it has to be smaller than that. And I'm not sure in the work that you mentioned, is it multiple?
Yes, most yeah, both which is that.
The thing, molecule has the electron spin.
Yeah, there's no question. There's no question.
Right.
So I don't know what can be happening with nuclear spins completely scrambled at short range, but then they have to come out as molecules, right? There's no, I mean, there's no out in any other way.
I mean, if that scramble completely, that it's don't scramble. At least to the reader check.
But that contradicts the definition.
Well, it depends on what they do the coupling is. If the coupling is very small, then
Gigahertz, well, short range, so change the hard frequencies of therapy completely change. That's
we
the-
had, you know, we had the experience, we had to explain it, so I'll put the wording on that.
Right, sure, but I mean, it may be that there's just some other symmetry effect that is equally there. Would also be interesting effect there. Just because they have to come out as fundamental modes, right? They assume the spin symmetry. They may not have spin symmetry, but they come out and then, okay, they realize, all right, I have to be symmetrical and asymmetric, and they just do it. They become, you know, something like that.
I think it was a matter of perspective.
Well, in the context.
I mean, I would say like they just can't change until some place, and if the coupling is strong, then they could change. But if the coupling is not strong, they're still spectator, right? So then the question is about how strong is that relation not, right? Like usually they don't do anything until there's coupling. Is my picture, it's not like they just start like, you know, what does it mean to be like that, right?
Yeah, okay, all right. Well, it's interesting, because the new correlations can shed some light.
Yeah, absolutely.
I see. Explain it, because some resembles like a brain transformation, right? Right, so the inside is a lot, and then it's going to be want to go out in a particular channel, so that someone do it with brain transformation.
Yeah, I'm just trying to reconcile those two. Also, to me, it's like a cognitive dissonance that when I read this paper and I read this paper of yours, it says scrambles here. not scrambles. Well, of course, yeah. Right. Well,
Yeah, but because the DT comes out, yeah, so I'd be, you know, interested in what the implication of the calculation means. So I mean, that's sort of fun, like, you know, we have to, experiment in theory has to go hand in hand, like, have to check one another and then continue the process, yeah. And ultimately, we hope to be able to share some light onto these other molecular systems that somehow their complex life is. You know, I mean, that's not directly measured, but it's implied to be very long. And why is that? And nuclear screen. If nuclear screen does not concern, maybe that, you know, let's say something is wrong, but here we show the nuclear screen is concerned. So the only way we can connect from one experiment to the other is through theory.
isn't what I thought that kind of what your model shows is that if you assume that the nuclear spin is concerned, you get those distributions, but there hasn't been any discussion of what if I don't assume nuclear spin is concerned, what would I get if that were the case? And you see, the model was great, it was predicted, but maybe.
Well, it will be statistical. I mean, if you say if it's statistical, then it will get a different.
There would be no, there would be distributions will go like up and down, but there would be just more structural, you know, compared to what you measure up very small population.
Yeah, I mean, but actually, so the parity of.
Yeah, the parity
The
would be
parity.
violated. That's a strong.
Yeah, I mean, then
difference.
the small population can be explained by the fact that we didn't really start in that basis perfectly like this, right?
Yeah.
So these can all be, you know, to what we can see experimentally. But we did, there was some kind of odd data from something else that did have a little bit of this kind of flavor, but I forget exactly what. That is not this way what we're looking at. I don't know, coincidence detections, you know, like that would give us even more information, because like, yeah, and I can't, I mentioned this to Jared, but I don't think there was any mention of that.
Okay.
Join me in thanking Kang-Kuen and so stop making it.
lunch is served, and don't forget to vote